Welcome to Battery Generation, your podcast on electromobility and European battery research. We all know capacitors from physics class. These little devices can store energy and sometimes they kind of look like a battery, right? Now, the Estonian company Skeleton Technologies, they came out with a SuperBattery, which is an innovative storage solution using the advantages of both a battery and a supercapacitor. A hybrid storage technology, if you will. Reason enough to talk to an expert about this. Welcome to Battery Generation, Dr. Sebastian Pohlmann. Hello to Tallinn, Estonia.
Hello, Patrick. Nice to be here.
Let me introduce you to our audience, Dr. Pohlmann. You are Vice President of Business Development at Skeleton Technologies. Skeleton is a developer and manufacturer of energy storage devices for transportation, grid, and automotive applications. We're going to talk about supercaps and batteries, about that super battery for sure you're developing over there in Estonia. But let's get our listeners started first of all with some basics at first. We all remember capacitors from school. Would you once more refresh our memories from physics class? What is a capacitor again?
Sure, no problem. A capacitor stores energy, but it stores much less energy than a battery. And capacitors store energy differently, and that's also why they store much less. They store energy via charge separation. That basically means that instead of taking the charge and storing it in some chemical reaction, you just take it and store it on a surface. That also means that you can retrieve it very quickly. And that means that capacitors are really powerful. You can charge them and discharge them very, very quickly. And same for supercapacitors. So capacitors, supercapacitors, really high power devices, can charge very, very quickly, but they don't have the same energy density as lithium-ion batteries.
So when you compare a supercap with a battery, you'd say the power density is higher with a supercap and the energy density would be higher in a lithium-ion battery, correct?
Exactly, yeah. And if you want to explore the ratio, so to say, then a lithium-ion battery has around 20 to 30 times more energy per weight than a supercapacitor. And speaking about supercapacitors and capacitors, there are also small differences there. Capacitors are really basic physical capacitors where you just separate the charges onto surfaces. Supercapacitors are a little bit more complex. They still work via charge separation, but they actually have electrodes which contain activated carbon, where they have a lot of surface area, and you make use of that surface area and phenomenon called the electrochemical double layer in order to store more energy. But they're also a little bit slower than capacitors. So you can kind of say that the classic capacitors, they react in microseconds to milliseconds. The supercapacitors work from milliseconds to seconds, and then the batteries normally work from minutes to hours.
Could you once more tell us how does a super or a capacitor at first, no supercapacitor, but a capacitor, how does that work and how is it constructed? I remember from physics class, it was basically two metal plates. But you're talking about supercapacitors that are a bit more complicated.
Yeah, they are a bit more complicated, and you're right on the two metal plates. And capacitors today are still those two metal plates, basically. Just replace the plate with a foil and then put a paper between the two foils and roll it up. And then you have two electrodes that are separated, and you can do charge separation on these two electrodes. That's a basic capacitor. A supercapacitor has, instead of the pure aluminum, it has aluminum foil coated with activated carbon, which gives it a lot of surface area. It's around a soccer field per gram of activated carbon that you have there. And then you fill this with electrolyte. And what happens if you apply a potential to this electrode is that all the oppositely charged ions in the electrolyte, so let's say you have sodium chloride, then you charge it positively, all the negatively charged chloride ions, they will move to that surface and they will form a layer on that surface. And that layer is called the electrochemical double layer. And in a supercapacitor, that layer is where the energy is stored, because again, you have suddenly two charges separated from each other, which constitutes a capacitor. But a capacitor stores more energy the closer these charges are. And in the case of the electrochemical double layer, these are atoms on the surface of the electrode. So it's very, very close. And that's why you have so much more capacitance, so much more energy stored in a supercapacitor compared to a classic capacitor. It's a little bit hard to visualize in a podcast. But it's something that you can really imagine a supercapacitor as two capacitors, two virtual capacitors in series.
We can talk about the limits of these electrodes. I have read something about ultra thin electrodes within a supercapacitor, but let's first of all distinguish between these terms: capacitor, supercapacitor, supercaps, I think is the abbreviation, and then ultra capacitor. What's the difference exactly?
So a capacitor is basically a classic capacitor where you don't make that much use of the electrochemical double layer. A supercapacitor or ultracapacitor is actually both the same. It's just that some companies used to call it ultracapacitors, some call it supercapacitors. We now have settled on the term supercapacitor, and we see that we make the distinction between the capacitor and the supercapacitor in a way that the supercapacitor makes use of that double layer for energy storage, which means that it makes use of this huge surface area of activated carbon. In terms of materials, it's normally easy to distinguish. A classic capacitor has a metal foil, bare metal, as an electrode. A supercapacitor has always activated carbon on the metal, so it's a black electrode.
And what are the limits when you try to make this pretty tiny, very small? I have read something about very ultra thin materials. What are the basic limits of the electrodes of a supercapacitor?
So there are, of course, a lot of limits similar to the limits of electrodes for batteries. So normally what you want to do is you want to bring as much material, as much active material that stores the energy onto the electrode. And for a supercapacitor, that means bringing as much surface area as possible onto the electrode. And that you do by using activated carbon. Activated carbon is well known in chemistry, but even in medicine or even in daily use, for having a lot of surface area, for having a lot of active surface area, where you can also use it for cleaning or something. Yeah. And if you bring this into a supercapacitor electrode, all you care about is having as much of that surface area available and bringing as much into the device as possible. So you want a dense electrode, which is still accessible to the electrolyte and gives a lot of surface area. Think of it like a sponge, but a sponge that is as compressed as possible and still offers you to suck up all that liquid that is the electrolyte.
You say it's hard to visualize since there is very few supercapacitors that you see directly in your everyday life. Nevertheless, there are supercaps within our daily lives, for example, in cranes, in buses and trams, for example, even in electric cars. Could you tell our audience, you at Skeleton, you supply a whole range of machine builders and manufacturers. Where do we see supercaps already nowadays in our everyday lives?
Actually, supercaps are used quite throughout a lot of applications. So the reason why you probably have not heard of them is that they are not used in the appliance electronics, in laptops or phones, or in the traction batteries of electric cars, where you always find lithium-ion batteries. That's why everybody knows what a lithium-ion battery is, but not so many people know what supercapacitors are. So supercapacitors are used everywhere where you need a lot of power for a short amount of time. And our supercapacitors are, for example, used in trams, the trams of Mannheim, the trams of Warsaw. Those trams already use our supercapacitors for braking energy recuperation. So the tram brakes, the energy gets stored. It's a couple of seconds only, and then it accelerates again, and you use that energy for acceleration. That is a classic supercapacitor application case. But you also have other applications in larger grid installations. So there are supercapacitor installations that go up to the megawatt range or hundreds of megawatts, where you use the supercapacitor high power to stabilize the grid. And that is then becoming more and more relevant the more renewables you get into the grid, because renewables are bad at stabilizing the grid. And if you think about, let's say, applications that quite straightforward to explain as well, is then it's mostly about braking energy recuperation. One application that is a good marketing application is what we're doing with Honda Performance Development in the US. They are using supercapacitors in a racing car for energy recuperation and then acceleration again. And that is, of course, the kind of ideal application for that customer, because they really want that extreme power when they accelerate the car. It's not necessarily an application that has direct implication on our daily lives, like the trams or the grid installations, but it's something very visible and very tangible in terms of what the supercapacitor can do.
Is there also supercaps within an electric vehicle? I could imagine these heavy machineries for construction, for example, mining, for example. Wouldn't that be a great case for supercaps within these huge vehicles that do mining, for example?
You're on the right track there. So anywhere where you need high utilization, where basically it is relevant that the machine works all the time and doesn't charge all the time, there it makes sense to think about these very high power devices that can charge in seconds or in minutes. So one application there is where supercaps are used today by our customers is intralogistics. So these are smaller robots that are working 24/7, so they're 24/7 in the warehouse, and they get charged within a couple of seconds while they stand still anyway. So they have a certain route through the warehouse, and at some point they need to stand still anyway, and then they get charged, and then they continue on their way. So you never have charging downtime. The same applies for large construction machinery, mining machinery, but we have to say there that the energy density requirements, so how much energy you can actually pack into a certain volume, are too high for supercapacitors for these applications. But at the same time, the power requirements are too high for lithium-ion batteries. And I think that's a good segue into why we actually were developing the SuperBattery, because the SuperBattery fills that gap. Yeah? So it increases the energy density while still allowing to charge in below 5 minutes or even in 1 minute.
We're going to talk about the SuperBattery in a while. There's a couple of questions from our audience that were asking me to, or asking you now to explain the difference between a hybrid battery and an installation where a supercap and a battery work together. But before we do that, I would love to ask you about the materials for supercaps. In this podcast, we mainly talk about battery materials, and I wonder, is there actually differences in the materials of supercaps, or is this probably a little bit more boring on the field of supercaps when you compare that to the battery technology field?
It's quite boring when you compare to the field of battery, because there's so much cleaner material mix in supercaps. You have aluminum foil on the electrodes, which is coated with carbon materials, and that is true for negative and positive electrode. Then you have a paper separator in between and an organic electrolyte, and that's it. There's no lithium, no cobalt, no nickel, no graphite, no copper, no heavy metals. So a supercapacitor is very simple in its material mix. In that sense, it's very boring, but boring is good if you think about supply chains, if you think about recycling, then you want boring. So supercapacitors in that sense are very sustainable, very easy to recycle. That's definitely one advantage that they have over the batteries.
As I understand, there is not much exploration and scouting for new materials then?
There is definitely some exploration. You have to understand that the market is much smaller for supercapacitors than for lithium-ion batteries, so there's much less money to search for new materials, to do more research. One thing that I can mention here is that Skeleton was actually founded on the idea of bringing a new material into supercapacitors. So our curved graphene material, which we have developed ourselves, which actually was the very first thing that the company even had as an asset, was that IP on the curved graphene synthesis process. That material offers more surface area per weight and per volume. And as I explained before, surface area is all that matters if you want to get more energy into a supercapacitor. And we are able to get around 72% more energy into the same volume of a supercapacitor with our curved graphene technology.
Is this curved graphene already part of the super battery? Could you explain that once more? What is the big mystery about this hybrid storage technologies where you combine batteries and supercaps? Is the curved graphene part of that?
Yeah, so definitely our curved graphene is part of the material mix, but it's not the only magic ingredient there. So what we do in the super battery is we utilize the existing electrode and cell design that we know really well from the supercapacitor. We know how to get basically high power out of a cell and out of an electrode, and we use a specific cell chemistry that we have developed ourselves. So we basically use a cell chemistry that we developed with the aim to have that very fast charging, still very good lifetime, and very high power, and combine that with the curved graphene. The curved graphene gives a benefit, but it doesn't give the benefit in the sense that you can only do it with curved graphene. You could also do it with other carbon materials. So it's kind of just something, a cherry on top, so to say, for us, that we have that material and we can use it here. The key development was the cell chemistry itself, though.
The super battery claims to charge in 60 seconds and last more than 50,000 cycles. If this was just a battery, of course, we would be highly skeptical in this podcast since we're used to battery technologies. But once more, could you introduce this battery setup, so to say, to us? Where would you put this super battery hybrid storage device into? What devices and applications do you see for the super battery?
Indeed, it's something that charges very fast. It has a lot of life cycles and still offers much more energy density than the classic supercapacitor. And where would you use that? If you think about time scales, then before I was talking about supercapacitors covering everything, maybe up to 1 minute of energy storage. And lithium-ion batteries are normally good for anything down to around 15 minutes. You notice this when you quick charge your phone or so, then the best phones maybe charge 80 to 80% in like 15 minutes or so. Yeah, the best electric cars today charge to 80% in around 15 minutes. So if you want something that charges much faster or that has a discharge pulse that is much faster, so in the range of 1 minute, 2 minutes, 5 minutes, in that area, then the super battery is perfect for that. And the applications that fall under this, there are a lot of different ones, but the one property of these applications that really describes them well is high utilization. So anything where you want that thing to work all the time, whatever you're talking about, whether it's a mining truck, a construction machine, an AGV in a autonomous guided vehicle, in an intralogistics application, or any other autonomous vehicle, then these things are supposed to drive instead of being charged. And in mining, we are working there together with Shell, for example, to integrate super batteries into large mining trucks where they get charged in around 90 seconds. We could charge them in 60, but you also have to think about the charger side. You also need that power to charge it. And then they are used for around 25 to 30 minutes. They drive around and then they end up at the charging point again so they can get recharged.
Now I come to this comment on YouTube by Gwyneth. She asks us whether the concept is combining a supercap with a battery physically. Let's say it's kind of like a hybrid installation within these vehicles, or is the concept rather you put a supercap on top of a battery and they work separately with another?
So there are two concepts though when you talk about hybrids. One is the internal hybrid, which is basically what our super battery is. You have a chemical hybrid. So it's one cell, one product that just performs that well. And you get to that performance by, like I said, you combine the kind of electrodes of supercaps the cell design of supercaps with the energy density of lithium-ion batteries in one cell. That's what you call an internal hybrid, and that's normally a new cell chemistry. That's quite complex to make, and we actually developed this over actually today over 8 years. Yeah, so it took a long time to develop this because you need to start from the cell chemistry from the lab. You need to build small cells and slowly scale up. There is, however, one other thing that you can do, and that's an external hybrid. An external hybrid is you take a known battery technology and a known supercapacitor technology and just use them in parallel. And that's more a problem for the electrical engineers to solve. Yeah, so that's something where you think about wiring, about DC-DC converters, and both of these concepts have actually their advantages in certain applications. If we talk about the mining truck, then you need that internal hybrid because you want to have both the high energy density and the power combined. So you want to charge the full thing in 60 seconds, let's say. If you think about a external hybrid, so you have a battery, charges slowly, and you have a supercap that charges fast, then you cannot charge the whole thing in 60 seconds because you always have the battery that still charges slowly. So when is this useful? It's normally useful when you have this combination in your power profile of a base load, the battery takes care of that, and you have very high power peaks, a couple of seconds only, that come in and go, where the supercapacitor can take care of that. So both of these systems exist, both are being worked on, and we are actually active in both, but they are for very different applications.
You sooner mentioned safety and stability of supercaps, especially your super battery. I could imagine that the stability, when you look at these cycles, 50,000, is probably a little higher than the typical lithium-ion batteries, but still, safety should be an issue since the power density is quite high. So how do you deal with that?
So the safety is one good thing about the super battery, that it carries over the safety of the supercaps. So the supercaps, as the super battery, are both extremely safe. You can punch a nail through a fully charged cell, you can overcharge them, you can overheat them without any risk of fire or explosion. So both the supercapacitor and the super battery bring this to the table, the very good safety. The reason for this, let's say, limited safety in lithium-ion batteries is often the choice of materials, but also often the energy density. So just having a lot of energy stored in one place is normally something that gets less safe and less safe the more energy you put in that one place. In the super battery, we chose the materials specifically so that we would have a safe product and that we could do the safety tests without having to worry about any fire or explosion. And that also means that we had to deal with some consequences in the sense of that we couldn't get to as high energy density as we initially thought. So you could get to high energy density, but then you have to deal with different safety topics, and this is not what we wanted. So we kept the energy density a little bit smaller, but have a very safe product.
This approach seems really interesting to me, to combine both advantages of a battery and a supercapacitor. But still, isn't there any downside? Is it really so easy to combine these two worlds? Is there any, let's say, disadvantage or anything that you're a little bit worried about to mention?
Now, first of all, it's definitely not easy. So any new cell chemistry development, as I said, is always you need to start in the lab, and it takes at least 5 years to get to some viable prototype, and that's also how we dealt with this. So we started this development in 2017, just on the idea level, and then we had the first prototypes rather quickly in 2000, end of 2020, 2021. We got the first prototypes. Now, if you talk about disadvantages, then of course the super battery is not the silver bullet of energy storage. It doesn't solve all of our problems. Let's say traction batteries in electric vehicles, they need energy density. They actually don't need that much power, and they don't even need that much lifetime. If you think about how much do you drive in over the life of a car, then today's lithium-ion batteries are very good at giving you exactly that. They give you the range, they give you the lifetime, and if you recycle them well, they can be quite sustainable. So while we basically are in an environment where you often have these very big written headlines of a new wonder battery has been invented, and I think that's not the thing to focus on, because any energy storage problem has its own solution, and there is probably one technology that fits it best. So you will end up with a mix of technologies, and super battery is just one part of that mix. What we are saying is that anything below the kind of 15-minute charge discharge range, super battery can add a lot of value there. Then you have the lithium-ion batteries that take care of the rest, and the supercapacitors that take care of the seconds to maybe up to 60 seconds. So it's important to keep in mind there's a mix, and there are certain solutions that are good for each part of the mix.
Let me compare your work to the battery research we are doing here. In our battery research in Ulm, one of the aims is to develop materials that last long as possible, that is safe, inexpensive, stable, easy to recycle, and of course can be recharged as quickly as possible. How is that with supercapacitors in general? How is the price? And once more, is the super battery recyclable?
If we look at price, then you normally look at price per kilowatt hour, and price per kilowatt hour for super capacitors. It's, let's say, no manufacturer of supercapacitors likes that comparison, because you normally don't buy a supercapacitor based on kilowatt hours, but you buy them to solve a problem. And your problem normally is not I need 1 kilowatt hour, but your problem is I need to solve that 1 power pulse. Why are supercapacitors relatively expensive per kilowatt hour? When I just said, okay, it's very cheap in terms of materials, you have aluminum and you have carbon, is just because you have so little energy density. So if you actually look at the price per cell, then a supercapacitor per just a certain volume of cell is cheaper than a battery. But in that volume, you have just so much less energy that per kilowatt hour, they are relatively expensive. But again, the customers that deal with supercapacitors, they normally know this. So they know I don't come here to buy a kilowatt hour. I come here to solve my problem.
But how much does it cost? Do you have any number for me?
I mean, the supercapacitor in terms of cost per kilowatt hour is around 10 to 20 times more expensive than a lithium-ion battery. Depends which lithium-ion battery you're looking at as well. Yeah, so, but that's the rough ballpark. And the super battery, to the second question that you asked, the super battery in terms of recyclability, it's actually quite nicely recyclable, because take into account the safety. So you can actually take that cell, whether it's charged, whether it's damaged, whether it's aged, you can take that cell and just shred it into its component without risking that it will explode. And then you can wash off the electrode mass. And since we use water for our coating process, we actually don't have to worry about any of the organic solvents or so on that would be needed for that. And you get kind of the mix of the anode and the cathode materials then. But we know from our suppliers that these can be actually separated quite easily. And we are also already working with our suppliers on a recycling concept. The good thing is that we don't have mixed metals. So we don't have aluminum and copper foil, for example, that we have to deal with, but we have just aluminum. So it's quite easy. You sort out the solid metal bits, and you have aluminum that you can recycle. And then if you recycle the individual components of the anode and cathode, then you have done your job.
Sounds good. Let's then talk about the production of supercaps, or your super battery. As you know, in the battery world, everyone's now talking about building up these huge facilities in Europe to produce for European markets. Skeleton is currently building a facility near Leipzig, Markranstädt, together with Siemens, and you guys are aiming to build the world's largest production facility for supercaps. What's the latest status on that?
No, the latest status is that this plan is, first of all, it's still the same plan, and it's still in the plan. So we are progressing quite well. The building is actually almost done now, and it's almost ready for the machines to move in. So we plan to start the production in the Leipzig factory, the super factory, how we call it, in end of 24. And the good thing about the supercapacitor production there is really that the supercapacitor cell design is the same as we use in SuperBattery. So we don't need to reinvent the wheel when we scale the SuperBattery in the same facility. We just put the same machines there and have two lines, one for supercapacitors, one for SuperBattery.
Yeah, you have to deepen this one since in the battery materials field, it's always hard to explain that a single cell is not always made for the huge market. Sometimes a single cell could be performing so great, but still for production, it's a disaster. So could you please explain that one for our audience once more? Why is that such a huge difference between a lab cell and then building up a production line that actually works at the end?
That's actually a huge component of being successful in energy storage as a company. You need to have a product that you can sell, but you also need to have a product that you can produce. So having the best properties in terms of the customers love you doesn't help you if you cannot produce it and if everybody in production is cursing at the equipment. So the thought that you need to have from the beginning already is this process scalable? When you coat an electrode in the lab, you need to think, can I scale this somehow? Would there be machines that can do this? When you build a cell and you have a certain process, how you build your cell or so on, you need to think, is that scalable? Can that be done with the processes that are industrially today established? And having myself been in the lab as well, then it's often something that you don't think about that much, but it's also not hard to think about because you can actually look at the videos. How does equipment look like? There is enough material out there where you can look at an industrial production of battery cells. You could figure out what are the processes, and you can think about yourself. What am I doing here in the lab? Does this actually make sense in the big production? When new things are developed and you already have an established production, it's even more important that you don't develop things towards processes that you would need to establish anew, but that you can use your existing processes, your existing machines. Because otherwise, you might develop the best product, but you have no machines to produce it, and you would need to invest more money to buy new machines. And then in the end, customers will not like this either because it will mess with the timeline, it will mess with the costs and everything. So keep always the processes in mind that you plan to produce with.
Is there any direct competitor that is also building these hybrid supercap batteries in the world? Is there any company that does basically the same than you guys are?
There are definitely a couple of competitors. There are definite producers of lithium-ion capacitors. There are producers of so-called hybrid cells. Sometimes it's hard to distinguish whether it's a battery or a hybrid cell or a supercapacitor, because often enough we have experienced that there are producers that write hybrid capacitor or even plain supercapacitor on a cell, but it's actually a lithium-ion battery. So that happens as well. In the end, you can only find out if you know a little bit about what kind of voltages you expect in a lithium-ion battery, what you would expect in a supercapacitor or a lithium-ion capacitor. But overall, yes, definitely there are competitors doing this. But we know that with both our production footprint in Europe and with the technology that we have actually a very good chance, or not even a very good chance, but we know that we are market leader because our technology is not only cheaper than the competition, but it also outperforms it.
Let's talk about the market at the end now. The global market size for supercaps was recently around 800 million to 1 billion US dollars compared to the markets of lithium-ion batteries, which is more than 100 billion euros. Of course, that is still small, but do you think that's going to evolve soon?
Yeah, it's definitely going to evolve. If you think about supercapacitors alone, then they are part of the energy storage landscape. And the energy storage landscape is growing crazily. So they will grow with that landscape. If you think about the general, let's say, high power segment, then there are some market studies that show around 4 terawatt hours of lithium-ion batteries being required in around 2030. So the market in 2030 being 4 terawatt hours. and there are other studies that say 6 or 5, but in that ballpark, then around a quarter of that can be attributed to high power applications. That means applications that have less than 15 minutes of charging, discharging, or applications that need more than, let's say, 2-3 cycles a day, which means that you need the long lifetime and the high power of high power batteries or super batteries or hybrid capacitors, anything that falls under that high power segment.
Thank you so much for your time and expertise. That was Dr. Sebastian Pohlmann from Skeleton Technologies from Tallinn, Estonia. Thank you so much. Thank you so much for listening as well. If you got any questions now, then comment below in the comment section or send us an email at hello@batterygeneration.com. Thank you very much for listening. See you next time. Bye-bye.